Welcome back to the Structural Engineering Podcast. This week's topic is one we've wanted to cover for quite a while, and that's structural glass. Most engineers interact with glass as cladding, storefront, or maybe curtain wall. But in some projects, glass becomes far more than an enclosure material. It can carry load, stabilize systems, span significant distances, and become a primary structural element. That opens the door to some fascinating engineering challenges around brittleness, redundancy, connections, load path, fabrication tolerances. If you've ever looked at an all-glass stair, facade, or a long-span transparent enclosure and wondered, how's that actually standing up? And what engineering goes behind that? This episode is definitely for you.
The Structural Engineering Podcast.
My name is Matt Soda. I work at RJC Engineers here in Toronto. I've worked for RJC for about 7 years now, doing feature project, structural glass, feature stairs, retail renovations, you name it. We've kind of, in terms of materials and interesting projects, we've probably worked on some of it. So, and then lately we've been working on more blast related projects too. So we're kind of getting into that as well in terms of glass design. And prior to that, worked in Detroit for a few years for an industrial engineering firm. And before that was a steel detailing firm for a few years out of school. So
that's a pretty broad selection. I mean, that's very nice though, because you get to see a lot of the industry. So fun to hear, actually.
Yeah, it's quite no 2 days or no two projects are the same. It's always interesting. Makes me want to come to work every day. So.
Yeah.
Well, Matt, thank you for being on the Structural Engineering Podcast. Max and I are super excited to talk about today's topic, which is structural glass, something neither of us have any ideas about. So hopefully as we go through these questions, they make some sense and we can get some good things from you. So to start us off, when we talk about structural glass, what does that actually mean in practice? How would a structural, we can think of steel and beams and wood and have a good, idea of that. But from a structural glass standpoint, what are we talking about?
I mean, in one sense, all glass, windows, everything are taking some amount of load. But I would say, like, to define structural glass, you're looking at something where glass becomes more of the primary load carrying element or is doing more of the work than, say, a traditional window. So you have, say, a thin wall or a glass beam holding a glass floor. That would be kind of structural glass. So it's doing a lot of the work. And, the connections are glass to glass or glass to steel. That kind of encompasses structural glass as an idea.
To dig a little more into the structural glass, is it physically different? And I guess they're both silica, what is it? SiO2.
Silicon dioxide. Gosh, my chemistry understanding peaked in 6th grade. This is also referred to as silica glass. We also make borosilicate for high heat and soda lime. That's the most common, holding the trophy for 90% of production in the US. Aluminosilicate is a nice one with high strength and high heat tolerance, but I don't think we use that one in structures that often. We have many processes also to strengthen and temper and laminate our glass. Many options we get to choose from, but a specialized engineer that remembers his chemistry figures this stuff out. We just need to know the strength available, deflection tolerance, normal stuff.
But is sort of a structural glass a little bit of a different mixture, or is this just a thicker portion of a window glass that can take a little bit of load?
It's the same glass, so it would be probably the same thing to some extent that you'd see in your windows at home or even a windshield in a car. I think where you see a lot of in structural glass, annealed glass is kind of what you think of when you think of glass. It breaks, you maybe get a crack in it. If it breaks into large chunks, that would be kind of annealed. Typically for structural glass, we're using tempered glass. So that's either fully tempered or heat strengthened, and that has a much higher strength than annealed does. So, that's where I guess we'd be using that more when you want to actually carry some load.
Have a question on the strength and the fragility, but I'm going to save this for longer. I think Zach's got something to say.
So for any of our listeners, where do you say you're getting asked to utilize structural glass? I mean, are people coming to you and saying, hey, Matt, we want the whole building to be out of glass? And you're like, yeah, no problem. Sounds good. Or what is commonly kind of driving the use of glass? Like what's the use case most common other than windows per se?
Sure, yeah. I would love someone to come to me and say, we want to do a whole building out of glass. That would be great. I think
Very
you
ductile.
see it. Yes, yeah, exactly. Not in a high seismic zone, maybe. But I think where you see it most often are projects with kind of a very strong architectural intent, or that they prioritize the transparency, kind of vision, say a cultural center, a museum, a high-end office building, podium, things like that, where you want a statement piece. The architect has a vision, and they don't want to kind of hamper it with a lot of maybe more opaque elements, so columns, things like that. So that's where you tend to see a lot of structural glass get used, specialty specialty structures and kind of statement jewel box pieces.
Are there any misconceptions that engineers typically have, or architects maybe, about the glass as a structural material? Right, I'm thinking of, for glass sake, like Crystal Palace is the first thing that popped in my head, like that World's Fair building in the whatever 1850-ish.
1851. I did pretty good on that. But check this thing out. There's a lot of photos online. Well, rendered photos, not that many real ones. 293,000 panes of glass.
And I have no idea how this can transfer any load around, but like magically it was able to. Are there any ideas that we are not quite getting right often, like new engineers working on glass?
Yeah, I think the biggest misconception is the fact that most people find or think of glass as a fragile material, that it's something, it's a mirror, it's a window, it's you see it crack, and you're like, oh, how can that do very much? But in reality, glass, yes, it's brittle, but so is, say, concrete, right? And we have methods to make concrete more ductile and kind of fail in a way that we want it to fail. And and glass as a material has an incredibly strong compression strength. I mean, it's upwards of 2 times that of steel in a lot of cases. But in tension, that's where glass starts to fail when it comes to fragility. So we have ways of working around that, and I think that that's the main thing you see a lot of people say when you do a skylight or something, that they want it, and it's very much, they add robustness to the glass, a lot of glass layers, because they think you need it. But in reality, you can do a lot with fairly minimal amounts, given what we can do today. So
I want to add something in here. We talk about this later, but this fits well with what we're talking about now. And we actually had just had a discussion with Joshua Schultz, Lightweight Structures book. Anyway, glass is very strong in tension and compression. The problem is we have some imperfections in glass, and that really concentrates the stresses. So similar ways, like when you weld aluminum, you're concentrating the stress at the point. You need to make your weld account for that and the basic aluminum strength. Anyway, it is strong in tension, but the minor imperfections, the little scratches, are super problematic, and then your glass breaks. But we have a way to solve this.
That's exciting. Well, I definitely fell into the thing that most engineers fall into. I didn't. That's amazing that it's pushing steel strength. Tension is a problem, but the fragility was a concern that I had when I was thinking about what questions I have for glass. Is I picture it being very fragile, and maybe I'm thinking about this wrong, but I'll learn.
Yeah, I'm glad to hear these things, because I visited Chicago once and went out on I was very high up in a building and went out on some glass that seemed very thick, but I was like, man, this might be brittle. I looked at my wife and said, I'm sure this will be fine. I'm sure someone engineered it. So I have full confidence in structural engineers, but yeah.
As a story for that, so some of the senior engineers here did work on those boxes. But we have in Toronto, we have the same thing at the CN Tower. So the CN Tower, there's 2 floors. It's not out over an edge, but it is a glass floor, and you can see below you. And one year we did have a company event there, and we're all up there, and somebody finds out that the principal in our office had designed that floor. And so every engineer in the group subsequently went over and started jumping up and down as many times as they could on that glass. And me standing next to the principal, I say to him, I said, is that, is it designed by it? And he, with no sweat on his brow, was like, oh yeah, like that's no problem. I wouldn't even, I'll sleep tonight. So, that's the kind of thing you have to deal with that. But
I could imagine that if like and you probably now fully understand that like the safety behind glass, but if you think of it from a glass bottle or a window that maybe you broke with a baseball growing up, and you're like, oh man, this could be quickly cracked, but I'm sure there's more, and we'll get into that, more engineering behind it. So kind of in that same light, what are the key mechanical properties of glass that kind of govern the design, but also from a general standpoint, stress strain curve, how do things like that look?
sure, yeah. So glass in terms of, we'll start with stiffness. So glass stiffness is kind of akin to aluminum, very similar to aluminum in terms of stiffness. And then stress-wise, like I was saying, so compressive. So theoretically, the molecular structure of glass is the same in tension compression, and it's incredibly high. But the issue is when you have flaws in the glass, you have scratches, you have different things at the molecular level or at the micro level that basically degrade the tension capacity of that glass, or the tensile stress capacity in that glass. So that's where you get issues, and that's always the governing issue when it comes to glass stress. So it's always your maximum principal tension stress in the glass that governs it, and it's fairly low. So what we'll do is we'll basically find ways to drive load into compression. When you temper glass, you kind of give it a pre-compression in the glass that can help overcome those tensile stresses, and it's really a matter of managing the tensile stresses in the glass when it comes to properties. So the other kind of nuance of glass, or the interesting thing of glass, is that it's probabilistic. So like the strength is probabilistic, where more or less we can say that like we're not certain that a glass panel will break at X load, where a steel beam, you might be able to say, with relative certainty that beam is going to hold X amount of load. But what we can say is that there's a very small probability that the glass will break at X load. And so that's how glass design is based on a probabilistic, based on probability. So we're usually in the range of 8 in 1,000 to 1 in 1,000 in terms of breakage for glass, from a probabilistic standpoint. And so we design for the stresses kind of associated with that.
Wow, that is very cool. My stats ability is far behind me, but in my head, the design of concrete, let's say, 'cause we just said steel, is also a little bit stats based, because the strength we don't know exactly, but we take a range. It is tested, of course, but we know it must be above this range, and the tension isn't tested, but we know sort of what it should fall about. Do we have sort of a higher safety factor in glass design, and is it applied like normal design that we are used to, or is it just its own thing entirely?
Yeah, the reliability of glass, and that's somewhat, to be honest, it's somewhat above my pay grade as well, when it comes to knowing the exact reliability of the glass.
I still have an outside understanding of this, but Ted Kramer had a great Structure Mag article about glass design. He mentioned the statistics base as well, and that in appropriate design, it has 1 in 1,000 chance of failure, or slightly higher. I looked up what else has these odds, and many things that I hope don't happen to me, they do. But one scary thing, double yolked eggs. Does this mean I'm bouncing on my glass bridge too much? I've had a few double yolked eggs.
It's definitely considered in terms of what stresses we use in design, and as an example, maybe is European glass design is probably, I would say, further ahead of North America when it comes to that. Their codes are kind of much more put together, and they tend to be the forefront of it. So the stresses that they use over there are in some cases higher than what we're using here, and it's mostly like a legacy issue in terms of the glass codes, and the glass design in North America is just kind of lagging behind that. And so like they've really worked through the reliability of glass as a structural material, and it's coming to North America for sure. And we see it, there's actually the principal in our office here is just co-authored a glass design manual, structural glass design manual, in working on the reliability, improving the reliability of glass design, and from that aspect. So it's definitely getting worked out, but yeah, I would say it's somewhat conservative to some extent, the glass strength at this point.
Yeah. That's really fun. We'll definitely link any glass design code style things in the show notes because I want to take a look at them as well. Give me back to the basics a little bit. Annealed, heat strengthened, and fully tempered glass. How do they differ structurally? And can you also sort of define those for me? Because I think my guess is not going to be that right.
Sure. Yeah. Annealed. So annealed is kind of your basic, I would say your basic glass, when it's made, what you see, when you think of glass, like I said. So when it breaks, you get maybe a big crack in it. It's not going to shatter per se. It'll stay where it is, and if it does break, it usually will break into kind of larger chunks, right? And it's a fairly low stress. I'm going to talk in MPa, but it's like 20 MPa for annealed glass. And then on the other end of the spectrum is fully tempered. So fully tempered, basically what happens is they take the glass and they heat it up, and then they cool it. They cool it very quickly, and the surface of the glass compresses, and you get like a pre-compression in the surface. And so the center is under tension, but the outside is under compression. And so because of that, because of the issue that we were talking about with tension, your glass strength is much higher now because you have to overcome this initial pre-compression in the surface of the glass to start creating any kind of cracks or opening up any flaws in the glass as you stress it. So on that end, you're looking at 80 MPa, something like that. Now, and I'm talking very general. We'll get into the stresses in terms of the durations and different things like that. But I'm saying like somewhere in 80 MPa for
that's a dramatic leap.
Yeah, so 4 times, something like that. And then heat strengthens kind of in the middle of the two, so it's just a kind of a slower process. I believe when you quench it, a little bit slower than fully tempered, so you don't get the same pre-compression on the outside. And so you're kind of in the middle in terms of the stress for heat strengthened. And then the thing with fully tempered and heat strengthened is once you break it though, so you break fully tempered glass, crack it, that's the glass you think of when you think of safety glass. So it shatters into a bunch of pieces, kind of pops almost, and creates like a small fine glass shards. And so from that aspect, that's why we try and pair those with laminates, so that if it does break or one piece breaks, you don't have glass shards kind of falling from a balustrade somewhere, or they all kind of stay retained. And then to that point, heat strengthened, when it breaks somewhere in the middle between the two. So it's a nice kind of Goldilocks area there where it breaks, and it's not large shards, it's not small shards, it's kind of in the middle. And so from a redundancy standpoint, that's nice, because when you laminate it, you can actually still get on the compression side, say if it breaks and it starts to flex and the compression is happening on the broken side, though the glass will interlock, and you can actually get some compression out of that in kind of a redundant post-breakage standpoint. So that one from a redundancy standpoint is a nice one to use if you can get away with the lower stress.
Is any common item heat strengthened? Like I know annealed car windows, right? We can kind of all picture those as broken. This heat strengthened sort of middle ground is anything that we use every day with that.
Yeah, anything you see that's got usually those stamps in the bottom corner that say like safety glass or tempered, like your shower door, let's say, that those are always like safety glass tempered, so that if it does break, it's gonna dice and you're gonna end up with not getting cut, not getting cut too badly, I'd say with that. So yeah. So those, that's everyday kind of usage of that safety glass. When you hear that, usually it's fully tempered glass.
So is one of these three that we've talked about one that you most commonly start with or you utilize? And I'm curious too, like from a price standpoint, they all seemed a little bit different, higher strength, more cost, or are they all kind of the same but have specific uses?
Nowadays, we typically tend to use fully tempered. And then heat strengthened is a nice to use if you can get away with the lower stress. So if you have areas where you're doing maybe something that doesn't have holes in it or point fixings, heat strengthened you might be able to make work. From a cost perspective, I think nowadays a lot of the fabricators and a lot of kind of structural glass projects, the expectation is tempered or heat strengthened. So I don't think you're seeing a huge huge jump between the two. You don't see annealed I would say you don't see annealed very often. In some curved applications, you might see annealed glass and some more like, residential windows, things like that, where they don't need to go fully tempered or they don't need to laminate it. But from a structural glass perspective, yeah, it's fully tempered, heat strengthened are fairly common.
Do you know what I'm just thinking through this in my mind, like what the manufacturing process looks like for any one of these, of like they get a sheet and then they lay it flat and they cut it or they curve it, or what is that? And I'm just like thinking through, all the materials and how we do shop drawings, and it's like, do they have to be particular on curves and just how it gets manufactured?
Yeah, it's you tested me a bit, but it's I mean, like from the start, you heat up, you get like molten glass, and they'll float it out on a tin line, and that's how you get that flat glass pane. And then from there, what you'll do is you'll heat that up, and then you do the quenching, and that's where you're going to get the pre-compression, and usually it rolls out on rollers, their line. And so the problem that you do run into with those from a architectural standpoint is that you can get what they call like roller waves. So because it's still a little warm, the glass, it does have a little bit of wave as it goes over those rollers. It'll start to deform a little bit, and you can actually see that in tempered glass sometimes. And so we try and control for that visually from an architectural standpoint. And then after that, there's a lot of finishing of the glass edges. So we always want to polish the edges, make sure that they're kind of chamfered, soften the edges so that we're not creating kind of stress concentrations at the edges of the glass.
Is there like typical sizes of glass, the thickness? Like, are you calling out the thickness of the glass and the layup of the layers of it?
Yeah, we're always.
Okay.
I mean, that's basically like specifying a wide flange. You're going with thicknesses, so they go. They'll go effectively in quarter inch, 5/16, 3/8, half inch, or if you want in metric, 6, 8, 10, 12 millimeter thicknesses. We're usually designing, so there's a standard for tolerance of glass thickness, and so we're always like in design, we're a 10 mil piece of glass is going to actually be like more like 9 millimeters in North America. So we're designing for the thinnest possible based on the standards. And then in terms of layup, like if you need a glass beam and it's got let's say 4 plies or 4 lights of glass in it, you're going to call out, we need these thicknesses, 4 of them. And then in the interlayers, we'll call those out as well as how thick the interlayer needs to be, the type of interlayer. And then you'll have a full kind of assembly, full glass package that is specified.
Dang. Okay. So going back to, the codes and stuff that you've mentioned, what are the codes we're looking at utilizing? I know you're up in Canada. Maybe you can talk about the code that you use there, but maybe as well in the United States that govern the design of structural glass.
So, I mean, IBC is obviously or the local building code. That's kind of where it would start, I would say. Like Chapter 16 speaks to, there's some deflection limits for elements that support glass. Chapter 24 is all about glass, the IBC. I can't say it's structural glass focused per se, but it gives a lot of background on use of glass. ASC 7 for all your loading, that's typical, just like every other material. And then referenced in the building code for the States is ASTM E1300. So that is, it addresses glass strength and behavior. Kind of the interesting thing. And so in Canada, very similar, we have our national building code. And that references, and there's a standard in Canada called CGSB, and that standard is since been withdrawn in '89, quite a long time ago, but it's still kind of the standard that we use, given it's the last printed code document on glass design in Canada. So we use that, and then, so E1300. That one is, the interesting thing about that is it's not really designed. It's designed more for windows. So it doesn't cover holes in glass. It doesn't cover point supported glass or even structural glass members. It is explicitly kind of says is not made for complex geometries and structural glass design per se, but that is the standard when it comes to stresses and in glass design in the U.S. And so to expand on that, the European design, European codes have a lot of good kind of references and ways to design structural glass. And so kind of coupling some of the best practices from those codes where applicable, and then the American codes. And then there's also a couple of nuanced ones for glass floors and like that one, like the glass box there in Chicago. So just so those all have to have a sacrificial light on them anyway. That's per that code. So if you ever drop a penny or anything while you're up there, you don't worry about that. That one's made to break the top plate. So there's a code for that as well.
Like, how do the ASTMs and ASCE interact? And more important, like, do HAs reference specific codes that sort of dominate, right? When we do a normal traditional design, like ASC 7 for us will kind of dominate. Like, all loads must be through that. We might have a unique case, but like we have this one dominant. In glass design, is there this is the primary code, but special items may be referenced by something else?
Like E1300 would be, I think, the code that most HJs would reference in terms of kind of looking at a set of calculations, let's say on glass. Like that would be what you would reference, and I think most would recognize as the standard. And then obviously like that's referenced through the IBC as a reference standard. So that's kind of a direct line between the two. And then ASCE for, again, all your loading conditions. And even there, ASCE does speak to glass to some extent in terms of like, say, seismic design and glass fallout of a frame and compatibility between glass in like in a frame system due to drifts and things like that. So there is a little bit of that in ASC as well. So I would say that those are all definitely what would be referenced. And then kind of sometimes first principle analysis of, very unique elements for, say, buckling of a fin, different things like that. You would probably have to go a little bit outside of typical codes, but, engineering judgment kind of rules there, I would say.
So is that where more of the performance-based kind of design comes in play with structural glass?
Yeah, for sure. I think like that side of it in terms of, you have the E1300 and you have the stresses and, some durations and things like that based in that code. But yeah, in terms of a dead loaded, fin or a cantilevered fin supporting a wall or that kind of stuff, you definitely be doing some analysis that's not kind of prescribed in any code per se, or you have to reach out to another code where there is a methodology for doing it. Even AISC, like the buckling for columns and things like that, or for beams, has definitely been adapted to some degree for like a glass beam buckling or a fin, things like that. So yeah, definitely that performance-based aspect of, and also from a redundancy standpoint too, the performance-based, like that's all not particularly codified in terms of wanting to design for redundancy, post-breakage analysis of glass, all that kind of stuff is a lot of best practices when it comes to that.
So you guys mostly, is there a software you guys are using typically, or is this kind of in-house spreadsheets, hand calcs? What does that side of things look like?
Yeah, mix of both for sure. We've got a lot of spreadsheets that we worked on to do kind of more work through glass stresses, holes in glass, glass fins, beams. The one software that's fairly dominant, I think, in the glass design is MEPLA, it's called, and it does. You can do a lot. You can do holes in glass. You can do four-side supported glass. A bunch of different interesting geometries and different type IGUs and laminated glass. And so that's kind of that's what you see most often when people do that from an FEA standpoint. And then we use some other software, just more general FEA to do kind of large deformation analysis on glass, just more for a compatibility. Sometimes if you have a frame and you want to see how it kind of behaves from that, say, buckling, things like that.
Yeah, the idea of glass buckling is a chaotic thing to me. Anyway, when I was young, I remember learning that in an old building, the width of the windows at the bottom might be a little bit thicker because the glass sort of flows or it creeps. How do you address creep effects in glass in general? And is this something that goes into design?
Yeah, that's I'm glad you brought that up because that's I can dispel that myth here for
No.
everybody. Yeah, so that glass as a material, it does have it has a very high viscosity, so it actually doesn't flow. And
Damn.
actually, one stat that I did see was that because of the high viscosity, it would take longer than the Earth's age to flow enough that you would be able to see it with your eye. So that's
So if we
how
waited long
slowly.
enough, though, it would.
There is a duration. Yes, there is a duration where you'd see it.
Okay.
And actually, yeah, and that so the thickness of the glass in those, I think they say it was based on spinning. It would spin the glass to get to kind of flatten it out, and that would create kind of thicker portions. And then when they cut it, they would usually drop the thicker portion to the bottom just because it was more stable than it was, having the thick portion at the top of a window. So that is that myth, but
I triple checked this online. Of course, Matt is right, but for the scale of this concept, we're about to hit the 100-year mark on the pitch drop experiment, or the start of it. Pitch, like the stuff on roads derived from coal tar, I think of as a soft-ish material, certainly way, way softer than glass. In 100 years, this pitch has flowed 9 drops. So if that stuff is soft, no, glass is not a liquid.
I would say that glass is a time-dependent material, but not due to viscosity. It's because of what they call static fatigue, and so that phenomena effectively, you have micro cracks in the glass, and they will grow when exposed to moisture and humidity in kind of in a positive opening stress at the cracks. So like as you have stress in the glass elevated and you have moisture and different things, that those cracks will grow it to a point where they'll become critical and the glass can break. So the longer you have a glass like load on a glass element, the lower that kind of stress that we designed for would be, just because we're managing that time dependent kind of static fatigue aspect of it. And coupled with that, the other duration item when it comes to glass is your laminates. So the laminates are what they call viscoelastic, and it's effectively kind of a polymer plastic material, and that is both time and temperature dependent. So it does at elevated temperatures, it has a lower shear modulus, and uh, over a longer duration, it will relax. And so, kind of long duration glass design, you have less of a composite action between your glass when you laminate it versus a short duration wind load. Let's say you can sometimes get pretty high, almost near perfect composite action to some extent, for at least for analysis purposes.
Sounds adjacent to the CD factor in wood design of like if you push very slow, it will yield. But if you
Yeah.
just have this quick thing, less so. All right.
Mhm.
The kind of curious about what load cases control, but by that I mean like, is there something unique that controls glass design that we wouldn't expect in the load combinations?
It kind of is actually interesting to some extent because the different loads kind of interact with glass differently. So you have, wind load is typically like a strength and deflection issue when it comes to glass, more or less. Seismic loads, to some extent, seismic loads are more of a compatibility issue, and sizing of joints and movements to not kind of, you don't want to bind the glass up. You obviously want to allow it to kind of move with the building rather than trying to resist any particular loads. And it doesn't have, in most cases, the self weight of glass, while it can be heavy, it's mostly carrying its self weight a lot of the time. So, its seismic acceleration is not huge to some extent. So that becomes more of a compatibility issue. And then, you have sloped glass or skylights. Those are, snow and live load, again, kind of stress based. But one that is big with glass too is thermal. So like
Mm.
thermal from a stress standpoint, what we don't want to do is lock in thermal stresses in the glass. So, in a glass pane or a glass point fixed glass canopy, let's say. So a lot of the time it comes down to detailing of the glass and making sure that we have, adequate oversized holes to allow the glass to expand and contract a little bit as the temperature, warms and cools, and or having, your perimeter of your glass kind of captured in a way that it does have a gap so it can move, it can shift a little bit without kind of binding up and causing induced stresses. So from a load case, you have your standard loads, but it is a lot of, there's the environmental loads of thermal, you have movements, you have tolerances, which is one, when you fabricate glass and you bring it to site, we really have to kind of be cognizant of tolerances because you can't recut glass on site like you can a steel beam, right? So you better fit when you get it there. And so from that aspect, it does come down to a lot of detailing and kind of dealing with kind of the connections of glass more or less when on that side.
When it comes to this type of glass, is there a lot of like manufacturers for it? I mean, I imagine in the world there's a lot of glass manufacturers, but for structural glass specifically, are you designing around more general and they go find someone that does glass, or do you work with the supplier quite closely in design?
Yeah, there's kind of a hierarchy. You have like your glass contractor who, will get the job, and they will, usually that glass contractor is not the one who fabricates the glass. So they'll buy it from a supplier who makes that all they do is make glass. And there's varying degrees of fabricators, sophistication of fabricators, definitely across North America and abroad. And then you have sometimes hardware suppliers. So there's people who are just all their bread and butter is supplying the hardware that supports glass structures, points, fittings, different things like that. And then the glass contractor will kind of try to bring that all together to kind of achieve a vision. But there is definitely there's a lot of places where you can get, I think, glass fabricated. There's very few places where you can get glass fabricated to kind of very high standards in terms of like a product, in terms of a very high end, let's say like jumbo glass, large format glass. There's very few suppliers who can do that. And so when you get that into that kind of range of very large oversized glass or very big laminates, sometimes it's only, one or two, maybe three suppliers in the world that can do that kind of stuff.
Wow. Okay, man, how interesting. What about one load that I know Max and I are excited and so curious to learn about, but impact loads. How do you design around that? Is there additional loading you might add to consider that, or the woodpecker that wants to knock down your glass almost?
Yeah. So like impact is, there's definitely like some language to it in the code on impacts, and it comes up a lot on balustrades. So like when you have a glass stair or walkway, something like that with glass balustrades, impact's a big thing because if someone bumps into it or somebody hits it with the side of their cart, something like that, that can be an issue. So a lot of the time we're designing around that in redundancy. So laminating glass, codified that like in a lot of cases it has to be laminated for that reason. So you break one, the whole thing's not going to break. And retain in the frame is one. So if you have a top cap or some frame that's kind of holding onto the glass in some way, that's better than kind of having a couple point fittings and no way to kind of keep the glass in place after it breaks. And then if you go further than that and you kind of go a little bit outside of more prescriptive design, it comes down to testing a lot of the time. Like you send a specimen to a test lab and they'll swing a shot bag into it and they'll hit the glass and see if does it break, does it not break. There's like rigid body, soft body impact tests. And so there's a whole gamut of those. And sometimes we'll have to just go that route to say, what, like we want to validate it, make sure it works. You can do some of that through testing, through FEA, but a lot of the time it's testing. And another extension of that would be like hurricane impact. So again, that one's a testing only kind of standard. They shoot a 2x4 at a window and make sure it doesn't go through the window. And that's a purely test-based method of analysis when it comes to impact. So definitely those are more test oriented for sure.
I like that that's the answer, because I'm, always think of like basics of structurals. You want to make sure you see it failing before it fails. And so if the thing's shattered and you're like, oh no, it's just, brittle and has failed, it's not good. So having that, sacrificial layer, maybe even in some cases, or you're not going to immediately fail. That makes a lot of sense from an impact standpoint for sure.
Mm-hmm.
I think about like windows. Denver International Airport has these really cool windows that are all point supported, and I remember a photo of not over Peter Rice, right? It's hanging on this like window that has these tension elements, and the glazing is point supported at the corners. How do point supported systems like change the load path compared to just a frame? And I know how it would structurally like just be point supported, but how does a window manage these point supports? And does it span between like, and you model this as creating sort of a beam element and then a web to it, or is it just entirely different?
Yeah, the point supported, it's just supported on those points, and it's allowed to kind of bend about maybe two directions depending on the aspect ratio and to those point fittings. Typically, point supported glass is, I would say, it's a stress. It's usually stress is controlling that design. Because you get these stress concentrations happening at the hole, right? In some cases, you're kind of bending at the hole, or you're bearing at the hole, depending on how heavy the glass is and which way it wants to resist the load. So you get these concentrations there, and it's really a matter of managing kind of edge stress and stresses happening in and around those fittings. And a lot of time you're making maybe the hole larger to help kind of reduce or increase the area where you can kind of transfer that stress. And we're making sure that those holes are, you get nice bearing in there with some more, going metal to glass. That's bad usually. So we'll have some sort of gaskets in there that are going to soften that up a little bit, or add some grout. Actually, is one thing we'll do, and add grout in the hole to kind of make sure you have even bearing all the way through. And so in that case, it's really a stress issue, and compared to framed glass, where that becomes a lot of time a deflection issue, because you're supporting it on four sides. You have a nice even uniform kind of supports, and you can distribute that stress a lot better in that kind of system. So
talking about deflections, what are the limitations of glass from a deflection standpoint?
Yeah, that would be, I mean, if there's a misconception about glass, I would say this is maybe the second one, is that like glass can't deflect. When it comes to deflection, IBC has deflection criteria for glass, typically glass frames. So they require certain stiffnesses for their glass frames. Depends on kind of the application. So if you have an IGU or like an insulated unit where it's a couple layers with an air gap in the middle, a lot of the time we're managing the deflection of the edge of those units, because from a serviceability standpoint, if you have too much deflection, what'll happen is you can break the seal, and then your unit starts to fog up, and it becomes just a maintenance and an issue from that standpoint, not so much a strength issue. So we kind of have stricter deflection criteria there. If it's just laminated glass or a monolithic piece of glass, in some cases, we're allowing Alon 120, Alon 100, but usually not to exceed the thickness of the glass is a lot of kind of the standard industry practice. You see it in kind of industry documents. And again, it becomes a practical issue. Like, you don't want kind of two pieces of glass next to one another deflecting and creating a gap now if it's deflecting more than its thickness. So we try and just kind of maintain reasonable levels of deflection from that standpoint.
How does that often work? Trying to think through. An architect comes to you, says, "Hey, we want to build this out of glass." What are things that architects are usually maybe not thinking of the right things to do with glass, or what are you pushing back on? Or I think Max and I could both speak to all the other materials of where we often find clashes with architects. This beam's got to be bigger, or something like that. What does it come down to in glass?
Yeah, it's a good question. I would say to think about it, probably like glass dimensions is one, like a big one, like I was saying, in terms of who can fabricate glass. Like we try and, you know, make a point of, right sizing the glass for the project. So, one nuance is like tempered glass. You can effectively only get tempered glass about 10 feet wide, more or less, a little bit over that. Anything wider than that, and they don't fit in the autoclaves that they kind of temper the glass in. So you can go longer, you can definitely go tall, but you can't go wide. And sometimes you'll see, an architect may draw an elevation and it'll have this nice big opening and it's all glass. And then we have to kind of make notes sometimes like, well, we have to break it up here. Maybe we don't have to have a support in the middle. If we can make it thick enough that it can just be two kind of butt jointed pieces of glass. But there's practicalities to fabrication when it comes to a lot of this stuff. And I think that's where you get into trouble sometimes, is like, how long can a glass fin be without a splice? Maybe another one, like you can't, over a certain height, you just can't fabricate it that large. So, it just comes down to kind of managing the expectations of like where you're not going to have transparency at the end of the day is like, it may be a big thing. It's like, where can we allow for connections? Where can we allow for a little bit of opacity in what is otherwise a pretty transparent facade or space?
The connection of the glass seems critical. It clearly is. Wire connections are often the most critical part of structural glass design.
They're definitely a more critical issue because, like we spoke about with point supported glass, you get stress concentrations usually happening at where you're connecting that glass. And so if you're trying to manage, like I said, more transparent facade, then you're going to have you want less kind of points of support if you can. And in that case, you're going to have kind of more stress concentrations in those areas. Definitely tolerances are one where you want to see, you want to allow for a lot of on-site tolerance in those connections, because your concrete slab is usually not 100% square and plumb and straight in all aspects. So you got to allow for some in and out tolerance. You got to allow for some movement up and down to accommodate all of that. And then again, from like the thermal aspect and kind of not over creating a situation where you have too much locked in stress and no movement in your glass, you definitely want to make sure that you can accommodate that in the hardware and the connection detailing. So, good connection design when it comes to glass is definitely a key when it comes to structural glass design. They go hand in hand with one another.
What do you say are like the common? I'm thinking too here, like from a sense of how you'd speak about glass. What are the common connections? What would you call them? If someone were to look at a glass structure, how would they know what the pieces are? And then, when you are jointing between things, I can't imagine it's just open into the building. So what are you, if it's trying to stay transparent, how are you filling those gaps so that things can move?
Yeah, so you would have kind of a common one you see a lot of are like point fixed. So you'll see sometimes what they'll call like a spider fitting, and you have maybe a couple legs that kind of come off a central node that's connected to, say, a steel structure or a beam or a column. You see it a lot in canopies. And then sometimes you can have some edge supported glass or some patch fittings where it's maybe a more discrete patch that kind of clasps the side of the glass and holds it in place along the side at different points. Or another one is a glass shoe. So where you kind of more so like along the top or bottom of the glass, this continuous channel that you might fit the glass in, and you see that in balustrade sometimes, kind of a continuous support at the bottom. And then a lot of it, and then so say in a glass fin application where you have a fin that comes into the building, and then you have a facade that's kind of perpendicular to that. A lot of time you see structural silicone. And so that the application for that is you can use structural silicone in a lot of different applications, but we tend to see a lot of those where you're siliconing the joints between two panels of glass. Maybe you're siliconing the glass to the fin. And a lot of time, that structural silicone under wind loads, resists you're in and out, inward and outward wind load on a building facade. So, you might see no frame glass, walking around and see glass with no frame. You kind of wonder how that's done. A lot of the time it's structural silicone bonded, whether it's to glass or to aluminum frame or steel member, something like that. So that's a big, really common one as well.
You had mentioned breaking a couple times here. How do engineers design for glass breakage and post-breakage behavior? If we have a bonded layers between, I'm sure there's quite a bit of strength remaining. How do you look at this?
Yeah, so we typically it's mostly like a risk kind of analysis, and that's the way that I think a lot of it's the way the European codes kind of look at it, in a way that the new kind of design manuals and things kind of look at it. And we tend to think about it in terms of where is the glass? Is it overhead of a public space? Is it, somebody walking on it, as we were talking about? Is it, off to the side and not really in a spot that it's going to cause a lot of, life safety issues? And then, what is it doing? Is it a primary element that's holding up, is that the primary load carrying member? Is it an infill piece of a structural wall? So all of that kind of plays into kind of a bit of a risk analysis of how critical that member is. And then from there, kind of think about, okay, so like we said, glass is probabilistic. So it's not so much glass will never break. There's a probability that it will. And so we design for that, knowing, there's a chance that it does, whether it's spontaneous, whether it's some impact, something like that. And we'll design with redundancy in the system, kind of make sure we have another load path to travel if need be, or post breakage condition of a panel or a light, or one piece of glass. We'll design it with that one piece broken. Say you have a fin with 3 lights of glass. So we'll design that fin in a post-breakage case with maybe reduced loading temporarily, with one of those lights broken. And then now we have to make sure that 2 of those lights can, say, take the dead load of the glass and some reduced wind load for a temporary condition. And then the expectation is obviously that something breaks, it's not going to fail catastrophically, and then ownership or of that building can kind of come in, brace it, make it safe, and then replace it in a way that in due time, so that you don't have any sort of issues. So that's typically how we're doing it, and it's definitely one of those. It's definitely something that's coming more and more in terms of the codes on the code side, but it is a bit of engineering judgment to kind of consider that as a case.
I feel like some of that answer may actually answer the question I'm about to ask, but I'm really curious. So what lessons have been learned from real world glass failures? And are there any sort of historic glass failures that we all know about, or that we could all learn about?
Yeah, I think the thing with glass is that I don't know that there's so many, well, there are glass failures due to overuse, overstress, for sure. I'm thinking of glass balustrades are one where you could point to a few cases where too many people leaning on a glass balustrade kind of back and forth, and it does break, which is quite sometimes an issue for sure. But a lot of glass failure, I think, happens not in a stress condition, but more due to accidental. So you have someone, someone bumps into it. You have during installation or during construction, the wall goes up and somebody drops a hammer or a bolt, and now you hit a canopy with it, and now you've broken that glass. and thermal stresses is one we see a lot, again, where stuff is to try in an effort to make something fit on site. Maybe something gets welded where it shouldn't have, and now you've locked in stresses, and then a glass panel maybe breaks because you got a hot day and now the glass expanded and it never go. And even one other thing about glass is, like, when you temper glass, there's something called nickel sulfide inclusions where you get these small imperfections in the glass, these kind of stones of material, and those can cause stress as the glass expands and contracts due to thermal, and it'll pop the glass and it just breaks. And we see it a number of times where a year or two into a project after construction's done, we get called back and, oh, that canopy panel broke. We go out there and you can see there's a telltale sign of how it breaks. And you can usually point to it and say, yep, that was, nickel sulfide. It's just kind of sometimes the price of doing business when it comes to tempered glass. There's ways to mitigate it, but, a lot of those failures of glass, I think, are not so much kind of structural or stress based, but again, it's more tolerances and making sure that, we're treating the whole design of glass holistically in terms of where we see the issues.
Yeah, I'm glad you went there because I was just thinking too, like glass, you probably got to get called out to more often than not. If from hey, this failed, it's a structural issue, and you go out there and it's like it's glass, something hit it, a rock, someone threw a rock at it or something.
Yeah.
Is that pretty? Gosh, I don't even know how to ask that question. Frequent, common, more so than other materials?
Yeah, I think so. Like, I think it's
Okay.
definitely, and usually because it's visual, right? Like you
Yeah.
see, beams and columns of a building is like usually they're covered up, and like you're not usually seeing kind of not that you're not seeing issues, but like a lot of the time, again, there's not a lot of damage that happens from environmental issues, but glass is so prominent usually, and a canopy above a doorway breaks, or a window, a facade glass fin breaks. That everybody notices that for sure. And so we do definitely get called fairly often for that kind of thing. And we do go out and we'll, do a whole assessment and try and we've done a number of kind of, we'll call it like forensic kind of more or less. I don't want to say we're forensic engineers, but I mean, we do kind of go through the whole process of we'll try and get the shop drawings and we'll model the system, and we'll try and add some thermal stress, see what happens, add a little bit of this, what are the loads, and try and go through the whole process of basically back engineering it all to make sure, like, was there a case where, we're overstressed or there's an issue, and try and suss it out that way.
And what about the maintenance and longevity of glass? Is it similar to all of our traditional structural materials, or is there you need to maintain it more one way or another, or seals need to be checked and connections should be checked frequently? And then would an owner need to or think to expect to change out glass, maybe like they would their windows? Maybe every 20 years I got to replace, expect to replace glass.
Yeah, I think glass in itself is maybe not the issue. Like you said, it's the seals, it's the connection points. I think that you definitely want to maintain it. Like it's a member of it's a portion of the building that does see kind of a lot of, if it's on the street, you see salt and you see exterior conditions and weathering. So silicone doesn't have a 50-year lifespan on it typically. So, silicone seals, you're going to have to replace every, number of years, whatever it is, 20 years, something like that. And then, making sure that you're maintaining, if it's a canopy, you're cleaning it every so often, not letting it get, dirty and gunked up and causing, maybe you get some dirt and debris in the fittings and it starts to bind, and gaskets, things like that. Because a lot of the time in the holes, you have silicone gaskets, or you have other things where, they can degrade after a while. And definitely maintenance is key when it comes to that kind of stuff too, to make sure that you can get the full lifespan that you expect out of that.
So I'm imagining that for the glass design of a building, it's maybe not typically always the engineer of record. It might be more of a specialty engineer that comes in and does the glass part of that. How early would you say, that the structural glass engineer should be involved on a project? And is that the right way to think about it? Is that there may be two different engineers?
Yeah, I think commonly, we've seen the whole spectrum of it for sure, but as like an overarching point, as early as possible, which I think you find a lot of people say about a lot of different disciplines, but it's definitely true. Like the earlier, the better when it comes to glass design. I think we've definitely been involved in projects where we're both engineer for the main structure and as part of the scope, we're doing glass, design from the consulting side. And what a lot of the time that involves is more of a performance-based specification. So where we'll come up with glass makeups and sizes and kind of concepts of connections based on back and forth with the architect and what their vision is, and try and really protect that architectural intent and make sure that we can offer something or tender something that is buildable at the end of the day, right? We don't want to just put something out there that, there's no way we're going to ever build that. But at the same time, we want to make sure that we're not giving too much leeway down the line to like have to change the system or really augment the architectural vision of the whole system. And so the earlier we're brought on and the earlier we can provide that feedback, like we were talking about in terms of, glass sizing and efficient load pass for glass, what kind of hardware we can come up with and detail out, I think the better your product is at the end of the day. And even from a base building standpoint, it's really nice when you're doing both, because we see it too, where on the contractor side, we've done a number of that type of work where we're brought on as the, specialty engineer, and there's a back and forth with the base building. And not to say that there was any miscalculation of anything, but like loads imposed on the base structure sometimes for these systems can get quite complicated. Think of a cable wall or a cantilevered glass fin, right? It hangs down and you have this load, and now you get this large moment happening at your slab, and maybe that wasn't really kind of worked through because the design was a little more conceptual during the design phase. And then we come in and we're providing loads now that you need to do some strengthening of the structure. And so, the earlier we're on, obviously that can all be caught ahead of time, right? We're doing those kind of calculations to say like, okay, we know that this fin wall is going to take this amount of load, or this, we have to hang all this glass from the second floor, and it needs to be pretty stiff because we don't want to allow deflection of the wall for a certain amount, over a certain amount. So, again, the earlier that we can get all that worked out and like have a system where we're confident that when we go to tender and we go to build it, it's going to get constructed in the way that the architect, intended, and the way that the owner, ultimately they're buying at the end of the day, and they get the product that they're after.
You mentioned a few, but are there any really common coordination challenges when you're not the EOR, especially like you just expect this thing to pop up?
Yeah, I think it's again loads on base building for kind of unique systems, deflections, like making sure that we have a system that's stiff enough for the system that we're providing. So whether it's glass, the edge support of glass, or if something's hung, or even if it's dead loaded and we have enough, we got to make sure we have enough deflection, between the wall and top of the glass to allow any live load. Like that kind of coordination back and forth is definitely something you see. And then just the same things that you tend to see with other materials, but glass in particular is, like I said, unforgiving on site, where, a slab is just maybe not, maybe it's in tolerance, but, or, a little bit out of tolerance, or a steel beam a column is a little bit kind of got some sweep to it, and just kind of those issues of making sure that we get a nice tight set of tolerances when we're working on that opening, right?
Yeah. And also sort of similar, but what field issues show up most commonly during installation? Would this be like slab tolerance or any building tolerance not aligning with glass? Is that a very common one?
Yeah, I think so. 'Cause it's just really, I think, a mismatch of constructability to some extent. Like, when you're building a concrete building or you're doing whatever it is, the tolerances of a concrete slab are pretty generous to some extent when it comes generous in relation to glass, where everything's quite delicate. Your connections maybe are quite delicate, or the opening, needs to be fairly tight because you are interfacing with architectural finishes at that point, right? You have your perimeter finishes, and you have kind of some details that maybe go along with that. And so usually that kind of stuff, when it comes to aluminum finishes and things, we're within millimeters. And if a slab is out, or eighth of an inch, let's say, if slab's out half an inch, then we're really going to have an issue when it comes to trying to interface the two. And it unfortunately is just part of doing business when it comes to the two. And you have to, like I said, you got to account for that early. And I think you got to make sure that you're thinking about that and working with the contractor early. And good contractors, like glass contractors, know that, and they've run into this before. And we've worked with some really great one out of Europe where their details are just tolerance. They've got a lot of the great glass companies are just all their details are just, they got movement X, Y, Z. They can do it all because they know that, like, once they get it there, they got to make sure that it fits. So
Thinking about more the cost side of things, what's the biggest cost driver in structural glass?
Definitely glass size is one. So there's kind of common glass sizes that you can get more or less for window glass, and as you start to go larger and larger, like I was saying, there's only you start to get fewer and fewer people who can actually fabricate that. So that becomes an issue. You have a couple suppliers, and typically they're overseas. A lot of them, there's one or two maybe in North America that can, but that becomes a cost driver for sure. A jumbo glass. Your interlayers is always a cost driver we see. So, the stiffer, more structural interlayers are typically a little more costly than kind of the more common interlayers for windows, and moving from one to the other, or having assumed kind of a less stiff interlayer versus one that you do need when you need a stiff interlayer, that can drive cost. And then complexity overall. You have curved panels. Do you have notches? Is it a cable wall? Is the hardware that you're using? Like I said, there's suppliers who can provide pretty somewhat common, like they have their own type, but there's the same geometries more or less. Versus, do you have to fabricate everything custom, and everything's all milled and created especially for this because it's a very unique situation? That also drives cost up as well. But in some cases, it's worth the final product. So
Yeah, I could understand that. Something just came to mind when you're talking through a lot of these complexities and thinking back to the question about code and the nuances of it. Is there any time an AHJ asks to get peer review done for the design of glass, or is it mostly just taken by the design? The AHJ says, "Okay, designer, you've done this, you've met these codes," or sometimes they say, "Hey, could you get one other group to look at this?"
I can't say I've been involved in any situation where that's been a real concern or a real issue. Yeah, I don't know that it's as common maybe as it is for unique building conditions, performance-based seismic design, things like that. But there's definitely times where, you might be designing outside of the code to say best practice. And yeah, you do see, you get questions as to like where in the code is this, or where is this kind of codified, and you kind of have to have some sort of basis, and that may be a peer review when it comes to like having someone else who understands this look at it and say, yeah, that's best practice and that's good design, right?
In the concept of emerging trends and what things are new that you've seen, are there any new maybe analysis tools or higher grade materials that is affecting the design principles of structural glass?
Tools, I mean, I definitely think that we have a lot of the same software that we've been using for a little while. It used to be hand calcs. Now it's this like I said, this FEA software. Definitely with some of the stuff that we're doing when it comes to blast design and different things, we're kind of using software like multi-physics software, fluid dynamic type stuff to actually model. Triple glaze units is one where there's not a lot of that when it comes to blast design, and we've been doing a couple projects where we're dealing with triple glaze and trying to model it and all the interactions, physical interactions, and trying to validate that. You see technologies like vacuum insulated glass is one that we see kind of keep hearing more and more about, and that's like a very thin IGU. This is like two very thin panes, and they vacuum out all the air in the middle, and you get a very, very high thermal properties for that. And so it's quite good when it comes to trying to insulate your building, and we're hearing more and more about that. And I think in a little while, we're going to see more and more of that happening. But different interlayers, kind of glass coatings, things like that are definitely also kind of new trends. I've seen some clear glass bonding two pieces of glass together with kind of a clear, not silicone, but it's kind of similar material. And that's another one where that would be very interesting to see, kind of, a lot of silicone's black or a different color. And so like clear to clear connections are something interesting as well to improve transparency.
I don't want to get to the end of the episode without asking about blast design, because you mentioned this a couple times, and this just feels like it would not match well with the fragility of glass that I picture. And I know I'm thinking about this wrong, but tell me a little bit about like the blast design that you're thinking about right now, how you're applying these loads, and like looking at the whole thing. Tell me about it.
Yeah, it's definitely another way to look at glass, and it is an interesting thing, because when it comes to the blast design, like you're really trying to harden the envelope of the building, and tends to be glass in a lot of cases, right? Like they still want, at the end of the day, they still want to see out of the building, right? No one wants a bunker for a building, and so it really comes down to managing. We know glass, you're likely going to break the glass in a blast event, and the inner layer plays a really big role, because it is quite flexible, and you can get a lot of tension, kind of membrane action happening. And so it comes down to making sure that we're allowing, the glass will break, and it's just kind of as strong as it needs to be to stay in the frame, or even in some cases project nominally into the building, but not all the way back, and it's managing kind of life safety when it comes to it. So, again, we're letting it fail, but you can get quite a bit of capacity out of laminated glass in a blast scenario. And then your frames obviously have to be kind of hardened for all of that extra load, but you get a lot of dissipation, I think, is the main thing, because it's so flexible. Those inner layers, you can dissipate a lot of energy, which is, in blast design, that's a key component, right? You don't want to take the load into the building. Just like seismic design, you want to allow it to kind of yield and reduce that overall load. So,
well, to wrap us up, what advice would you give a new engineer that's interested in getting into glass design, or even maybe, more senior engineer that's looking to make a change?
Seek out, there's plenty of resources for sure. I think we've talked about a lot of them. Seek out those resources, kind of get familiar with the uniqueness of the material. You don't have to get into all the nitty gritty nuance of how it's fabricated off the start, but definitely kind of get familiar with it, and don't hesitate to kind of ask questions and seek out advice on it. It's definitely something that's not as common. So, but I think everybody that I've ever talked to who does this, is very eager to talk structural glass, the nuances of it, the cool things that you can do with it. So it's definitely, seek out, that side of it. And there's plenty of people who are interested in it and would love to help. So,
well, great. Well, Matt, thank you so much for joining Max and I on the Structural Engineering Podcast. I know I've learned a lot and excited to hear back from our audience. So thank you so much for your time.
Yeah, thanks for having me, guys. I really appreciate it.